We are live. You can start.
All right. Okay. Good morning, good afternoon, good evening to you all. Once again, I'm Mikailu Nadro. So today I'll be presenting on multi-party computation. But before I do that, I'll briefly talk about Dora Dojo and what they offer. Right. So what is Dora Dojo? Um, Dora Dojo is an open source knowledge community that is that is focused on cutting-edge technologies such as encryption and Web3, co-built by hackers. Dora Dojo regularly organizes knowledge-sharing sections in the form of live broadcasts, audio, and text. And the topics covered are from L1, which is the layer one, layer two consensus algorithms. I have the architecture as well, related content in GitHub reps, and we also have some topics covered in Scroll, zkEVM, Hygiene Hybrid, we have Aztec, we have Optimism, Aptos Move, and cryptography in general. That's under the ZKPs, Zero Knowledge Proofs, Public Key Encryption, Hash Functions, and many others. So that's like an overview of what is going on there. And of course, it's all hosted on the DoraHacks bounty web. So let's quickly run through the websites of DoraHacks. So in the website of DoraHacks, you can register, and here's the bounty page. The bounty page, you can see plenty available bounties. These are available bounties currently going on. You could see Codex, Elliptic Corps, Arcway, Evmos. We have up to sleeps with the, of course, if you can solve the research or whatever the task of the bounty is, you get your reward. So briefly, so that's the overview of the whole thing. Now, this will take us back to the topic of today, which is multi-party, secure multi-party computation. All right, open it in presentation. Okay, so we'll be looking at 3 points in our outline for today. First one we'll be looking at the concept of secure multi-party computations. Second one will be explaining the general definitions of secure multi-party computations and the different protocols of MPC and also their techniques. Then the third and the last one we'll be looking at sharing MPC, use cases, the limitations, and also the advantages. All right, so we'll be taking the first point, which is concept of secure multi-party computation. Right. So in the last decade, data privacy and security has become the primary concern of everyone. So now, due to this rise in the technological advancements and the internet, it has been a challenging task to provide data security and data privacy of the data which you have. So when data is distributed over large distributed networks as well, as everyone is now concerned with their data, a lot of research is going on how to provide data security and privacy to the participants in the network, like you and I. Now, one of the techniques which provide solutions to the problems of data security and also the data privacy is the secure multi-party computation, which we'll be looking at today. Now, the secure multi-party computation may be defined as the problem of n players. These n players we don't know them, so it's just n to compete jointly on an agreed function securely on the inputs without revealing them. I lay more emphasis on this without revealing them. Now, the aim of this secure multi-party computation is to enable parties to carry out such distributed computing tasks in a secure manner. How? This secure party computation is concerned with possibilities of deliberately malicious behavior by some adverse entities and some people that are not honest. These have also been considered in the distributed literature, where they are called the Byzantine faults. This is it is assumed that a protocol execution may come under attack by an external entity. So let me quickly this right. So the aim of this attack may be to learn private information or cause the results of the computation. Basically, why are they attacking you, or where do they want to get your data? So most likely they want to get like private information from you, or to cause a result of the computation to be incorrect. Maybe they want to mess around with the information that is on. They don't want it to be seen, or they just want to corrupt it. So now, two important requirements on any secure computation protocols are privacy and correctness. Now, for the privacy requirements, states that nothing should be learned beyond what is absolutely necessary, of course. And more exactly, parties should learn their output and nothing else. So the correctness requirement now, we've spoken about the privacy. Now for correctness, the correctness requirement is that each party should receive its correct output as it should be. Okay, here's a brief pictorial view of the whole explanation, the overview of how it works. Now, the secure multi-party computation provides a protocol where no individual can see the other party's data while distributing the data across multi-parties. It enables the data scientists and analysts to compute privately on the distributed data without exposing it. How? You can see it in this picture over here, where you have your X, your W, your Y, and Z. So this explains how uh, a particular data can be transferred privately without other people seeing. Let's say you have your data, you want to like get it across without other people seeing it. This is a perfect system for that. And people seeing or actually knowing it from you is one of the things. So now the co-workers want to compute the maximum salary is a use case. Co-workers want to compute the maximum salary without revealing their individual salary to others. This is just a perfect example. So to perform such a computation, secure multi-party computation is implemented to calculate the maximum salary. Now the parties in the distributed manner jointly perform a function to calculate it without revealing the salary. Now data in use is kept in encrypted form, broken up and distributed across parties. So in this way, they will know, yeah, this particular information from this person. When it's just broken up, it's encrypted. It won't make sense as such at the moment. Then until when all the data, all the information are like coupled up back to the owner, who can actually see, yeah, yes, this is actually my data. That's the output that you will receive. Now, it is impossible to have a trusted party in the real world. That's just the truth. And as all parties communicate with each other in one or the other way, in such a scenario, the parties may get corrupted. And corrupted parties have behaviors like basically we can classify their behaviors into two. We have the semi-honest and we just have malicious behavior. Those ones are just outside, they're just there to cause havoc. Now, the first one is we are taking the semi-honest. Now, a semi-honest opponent is one who follows specific protocol but make the party corrupted. The protocol is run honestly, but they try to extract information from messages exchanged between the parties. And we take the second one. The second one is just outright malicious behavior. The malicious adversary makes an attempt to breach security and does not follow the specific protocol. As I said, it's just out there to cause havoc. And the adversary can make changes during the execution process of the protocol while using the multi-party computation. We assume the party is honest, which follows all protocols. That's one of the downside of this. Just assume that anyone using it is an honest party, but that has to change. And we'll look into that. So now we'll be looking at the next point, which is explaining the general definition of secure multi-party computation as MPC and different protocols of MPC and their underlying techniques. We'll look at that briefly. All right. So the definition paradigm. A number of definitions have been proposed, and these definitions aim to ensure a number of important security properties that are general enough to capture most. Now, these are all important. We look at them. Uh, we now describe most of the central of these properties. Here are the properties now. We have privacy, we have correctness, we have independence of inputs, we have guaranteed output delivery, and we have fairness. All these properties have to be inbuilt into this MPC for us to have a moving a more structural architecture, right? So now look at the privacy. No party should learn anything more than its prescribed output. Yes, in particular, this is just to reduce the risk of having more dishonest parties or adversaries. And the second one is the correctness. Each party is guaranteed that that the output that it receives is correct. And we take a look at independence of inputs. So for the independence of inputs, corrupted parties must choose their inputs independent of the honest party's inputs. Then guaranteed output delivery. Corrupt parties should not be able to prevent honest parties from receiving their output. Exactly, this is very important. Then fairness, which is I feel this is very, very important. Corrupt parties should receive their output if and only if the honest parties also receive their output. This is also basically what fairness is. The same treatment for everyone, be it an honest or a corrupt party. Now, the ideal model and using MPC in practice. The ideal paradigm for defining security activities has some very important implications for the use of the MPC in practice, and some are specifically highlighted earlier in the property as you to understand it better. And now, in order to use an MPC protocol, all the practitioners need to do what they need to do to consider the security of their system when an incorruptible and trusted party carries out the computation for which MPC is used. So, all right, sorry for that. Okay, so any inputs are allowed. And second one is MPC secures the process but not the output. That's something that is highly misunderstood. Another one that is often misunderstood is that MPC secures the process, meaning that nothing is revealed by the computation itself. However, this does not mean that the output of the function being computed does not reveal sensitive information. That is just it, because you don't really know how it's being computed. Some of the data it may reveal some of the let's say personal information that you may not want others to see, and that's one of the downsides. Now, the underlying techniques of MPC. The first one is the shaman secret sharing. This is a common one. The secret sharing is utilized as the basic tool when there is an honest majority in secure multi-party computation. A secret sharing scheme is that a secret is shared among the n parties. As we said, there's the n parties because we don't know them, denoted as n, such that t plus 1 or more parties come together to reconstruct the secret. The parties lesser than the t cannot get any information or reconstruct the secret. Then the scheme, which fulfills the requirements of the t plus 1 out of the n, is called the threshold secret sharing scheme. So with this, kind of give you like a little border between the thresholds that you can pick or kind of see. So this way, the secret sharing is kind of limited to a specific number of persons, and those that can view and those that can't. Second one is the honest majority entity. The function can either be represented by a Boolean or an arithmetic circuit in an honest majority. Now, for the MPC-based secret sharing, having honest majority, there is a finite field, that's a ZP, with P greater than N for an arithmetic circuit, and the circuit is Turing complete. This is a mathematical model that explains it better, um, relating the honest majority and the Shamir secret sharing. And the third one is the input sharing. Every party shares the inputs using the Shamir secret sharing, and the circuit is being provided the input for computation. Every party keeps its input private by adding some random number to the input, and finally, after getting the output, the random number is known to the party. The random number is known to the party. Sorry, the random number that was known to the party that added it is being removed, and we get the output. Meaning, let's say you added that particular number, you added that particular number, maybe to make it look the data to be more uh, rather encrypted. So when it comes back, the system already knows the data you inputted, right? So the output you are getting is where you inputted, and that value added will be taken out. Can only be viewed when it's being shared, but when it's coming out as an output to the owner of the particular data, that added value is not seen there. So the fourth one is circuit evaluation. So I'll just briefly talk about the mathematical setting. So you can see it's classified as Ci, which is equal to I and A and a function of I and plus B function of I. Simple and similarly, the output of the computation for the ith party is calculated as Ci, that's C of function of I, then A multiplied by B, in this case, not plus. Please for multiplication output. But the first one is addition output. You can just give it a value, it gives you an iteration of the I. So that's why it just represented it as I. It can be whatever value, whatever amount of input you put in to do the computation for you. Now the private set intersection protocol is very efficient for two parties problems. So two parties who wish to find the element of intersection with private set of inputs without revealing the inputs. As say you and someone, this is the perfect one for you. Let's say two of you, you have you want to rather um there's a set of intersection where you have two party problems. So say you and another person in this case, and you wish to find the element of an intersection, right? So the private set of inputs are there to be put there in the system without revealing the input because of course these are private sets. And then the private set intersection is better approach for both honest and dishonest adversaries. And the sixth one is the threshold cryptography. This is highly used in the crypto world as well. The threshold cryptography aims to carry out the cryptographic operations for a set of parties without holding the secret by any of the single party. So the RSA algorithm is used for the scheme where the basic function is y equals to x mod modification and RSA is used for encrypting secrets or messages. And we have the last one, which is a dishonest majority MPC. This is key. In the secure multi-party computation, they can be both honest and dishonest parties, of course. And now, the secure multi-party computation is secure as long as there is an honest majority. If the adversaries are corrupt more than the majority, new approaches are required for security. That's when you have when you have a rare case where the there's more dishonest parties than honest parties. Then there's another approach to take. An extra approach is taken. So for the dishonest majority, there are protocols like GMW. You could look this up. Oblivious transfer. Then we have the Gavo circuits. We have the Tini OS and many more. The last point, sharing MPC use cases and its limitations and advantages. So look at the use cases. The use cases, the following examples of MPC applications or use cases have been deployed. This is the first one, the Boston wage gap. The Boston Women's Workforce Council used the MPC. This is an actual use case in 2007 in order to compute statistics on the compensation of the one 1,600 166,705 employees across 114 companies, comprising roughly 16% of the greater Boston area workforce. The use of MPC was crucial since companies will not provide their raw data due to privacy concerns. You see, it's a huge use case. And the results showed that the gender gap in the Boston area is even larger than previously estimated by the US Bureau of Labor Statistics. This is highly important because there's always that bias when you see the data, but when you don't see who it belongs to, things like that. Yeah, a lot of use cases can be used for this. Now, privacy preserving analytics, right? So this for machine learning users is increasing rapidly. This is a known fact. An NPC can be used to run machine learning models on data without revealing the model. This is very important. To the data owner, with the data owner and without revealing the data to the model owner is a huge risk. You reduce the risk of the other party knowing about your data and vice versa. You can still work together. Okay? So NPC use cases continue. Yeah, these are other use cases like advertising conversion, the government collaboration. Drop the link for the material to read further. Right. And also this is a huge one. This is a huge use case. MPC for cryptography keys. protection. It's also used in the cryptographic world for um, software wallets for storing your crypto. And a use case is for the private key where it's being held in a single place. Let's assume in your cold storage wallet. This could be used. Okay. Now we look at the advantages. We have a trusted third party. So in the MPC, we share data in distributed manner with different organizations without any third party. This is one of the advantages. You don't need a third party. Second one is data privacy. The data is secured. The private information is secured. Is a non-fact. And the private data of organizations can be shared for computation purpose. It can be shared for computation purpose, and at the same time, the data can be concealed. Private data will not be revealed. This is just good. Then the third one, we have high accuracy. MPC is highly accurate, and it runs lots of computations. We are talking about the end, like thousands of computations. In this case, the third one is using cryptography. And the fourth one, quantum safe. The data shared between parties is safe against quantum attack as the computer is broken. We said quantum attacks can break any kind of system. So let's see how long it will stay. So what are the limitations? One is computational overhead. To provide the security, we need to generate random numbers. Like this is a problem. Now the random numbers, the random number generation requires more computational overhead, which slows down the runtime. So this is a serious problem. The second one, you could imagine all these random numbers. It's not as if you actually need them. Your data is concealed within. So you just have to go through it, and it slows down everything. So it's not nice at times, especially you have larger data to conceal. So the second one, high communication costs. Yes, distributing the data to multiple parties for computation over the network leads to higher cost of communication. Lot. So stressful when you have more parties to deal with. Right. Thank you. So I think with this, we have learned something about secured multi-party computation. And here are some of the references that you could Teresa Nawaz Mala in 2021, Yehuda Lindell in 2020 wrote about the secured multi-party computation available. Good. Let's go to one of the links and open it. Right. Thank you.